This late morning session's theme of Norwegians talking about things which are not necessarily Norway.
Prefer that, yes.
I'm very pleased to hand over to Asgeir to give the last presentation of the day.
Thanks a lot. Yeah, so this is joint work with Christian Skar, who is now an associate professor, 20% at NTNU, and then work in industry, and Hector, who is a PhD student in Trondheim, just finishing his work on this type of modeling, and two master students that actually did most of the computations on the long-term uncertainty in this model. And apologies to those of you who have seen it before. It was presented in the Transatlantic Infra Day in Washington just before Christmas, and we are writing up a paper on this now, so we are trying to work through and verify the computational results, because when we publish this, because this is fairly large models that comes out of combining long-term uncertainty and short-term uncertainty into this type of studies, and we want to verify the computations one more time before we publish it. But I think the outline is sort of pointing at some of the main challenges that we are facing all over the world, but in Europe, mainly trying to make the energy system before 2050 a zero-emission energy system, and basically that means that emissions in the power sector has to be reduced dramatically before 2050. So we have assumed 90%, and we are using an approach called multi-horizon stochastic programming, which combines short-term modeling and long-term modeling to do this. And in fact, for the first 10 years that we did this empire model for the European power market, we only included short-term uncertainty, while this is the first study where we actually do a full-scale study of the European market, also with long-term uncertainty included. So it took us 10 years actually to go from the ambition to what we have been doing now. So the first study I present to you is just to give a feeling about what this empire model could do in terms of power market analysis, including all the short-term analysis, and then we combine that with policy uncertainty in the second case study. So there are some references in the end. There's approximately 10 papers that we have published or have in writing on this type of models. Apologies for not having so many references to other people's work in the presentation, but there are quite extensive reference and literature reviews in those 10 papers on the literature. But I'll point at some areas where I think that there is not so much literature to find, and I would be very interested in hearing your experience on that as well. So some of the main challenges would be going to a zero-emission power system. Should we focus on the centralized solutions like transmission and carbon capture and storage? Or should we go for local solutions, which could be storage combined with like batteries, combined with demand response and flexible consumers? And we try to include that in this type of model, and that's also the reason why we need the two time horizons, the investment horizon, which would be typically 5 years, and the short-term time horizons, which would be a sequence of representative hours. And then we have the clean energy package of the European Commission saying there is much hope in the active consumer taking part in the markets, but there's a limit to what an active consumer can do, as we will see in the results. And in this outset, it's basically this is the power sector and this is the emission reductions we foresee. This is an old slide. I'm not sure it's much more optimistic these days, so the current policy would give us not what we're looking for, but I think it's fair to assume that the power sector needs to go to zero in the next 35 years. And the question is, what kind of technology mix will we see in the power sector under this assumption? So the empire model is aggregating. It could have several nodes per country, but in the current version we have one node per country, and then we have import-export capacities between the countries, and both the generation capacities of the different technologies and import-exports are part of the decisions that the model will make. It's a cost minimization capacity expansion plan for Europe, and it gives detailed technology mix per country, and it also clears the market hour by hour, not for the complete 50 years, but for something like 10,000 hours distributed over a number of scenarios, and these years until 2050. So it's perfect competition. In that respect, a naive model, assuming that Europe at the country level is actually cooperating to build the best possible and most efficient energy system and power system. I think this is in time happening in the market integration in the short run, but there are no signs that this will be happening on the investment side at the current stage. It says inelastic demand. This is not completely true because we add a demand response, so that means that there is demand response that could alleviate the critical issues in the short run, hour by hour, following some rules. It contains investments, lines are independent, and perfect foresight about fuel prices, carbon prices, and load development. That is in the short-term uncertainty model. We also implemented long-term uncertainty on those, but we didn't find very many interesting effects, so that's a different talk, but I'll not talk about that, but I'll talk about the policy uncertainty. So a little bit about what do we mean by long-term dynamics? Well, we mean that investments happen over time, so it's not a here and now decision, it happens in a series of and sequence of decisions. That's what we mean with long-term dynamics. So if you add long-term uncertainty in addition, that would mean that there are some uncertain parameters under which these decisions are made, and that could be policy uncertainty. So we could have a deterministic model with long-term dynamics, but we end up here in a model with long-term dynamics and long-term uncertainty. So we have the short-term dynamics. By that we mean there's a sequence of hours where we could manage a storage, or we could plan in a weekly horizon. You could plan your generation capacity and how it's used, and your storage capacity how it's used. And by short-term uncertainty we mean we add some stochasticity on the availability, for example, of solar resources and of wind resources in this setting. And that's the setup. I like to show this picture. It's a beautiful island of Crete at 5 o'clock in the afternoon. There is no wind, the sun is going down. This is an island, and it's going to be a zero-emission power system. Europe is also an island, if you look at it from that perspective. It has some links to the rest of the world, but we have the same challenge in this perspective. And this is a picture of Europe showing the wind conditions, and when it comes to wind, the green parts are good. So you would like to build wind in parts where it's green, and this is included in the model, so you have the geographical characteristics. It's a lot of wind built in this area, which shows just that we are probably not investing in a perfect competition manner currently. We have the similar for solar, and of course we have some very good regions for solar, so red is good in this case, and green is not that great. And again we see the investments are happening also very much in the green areas. So just to tell, this model looks at the geography and it makes optimal decisions given the input that it gets from a perfect competition perspective. So it would rather build solar where the sun is shining, but it also turns out it builds solar where the sun is not shining that much. And this has all to do with, of course, moving energy and the correlations. And in such a model, that models the technology mix, so this would be nuclear, coal, natural gas with carbon capture and storage, and then the renewables with hydro, wind, offshore wind and solar. So you get an involvement of the technology mix over time with capacity and generation, but then of course the generation comes from these representative hours, hour by hour, that is modeled in different short-term scenarios. And all of you that has been working with stochastic programming realizes we end up with a scenario 3, something like this, where you have long-term decisions, you have some uncertainty gets resolved, and you get one short-term scenario, then you have resolving long-term uncertainty, and you make a new long-term decision as you get more information about that. And you have this interchange between long-term and short-term uncertainty, which makes, of course, this tree explode, even if you only have 2 branches at each node. And the recognition we made maybe 10 years ago when modeling the natural gas networks in the same way is that what happens in January of 2020 is not necessarily relevant in terms of describing the uncertainty of what happens in January of 2035. So there's a disconnection between some of the information we have in those types of models. That means that we do what we call the multi-horizon approach. We say there's an end of horizon in the operational setting after a season. And then we start over again with a free-coupled description of the short-term uncertainty. And that means that in this model you will see the end of horizon many, many times from an operational perspective, but not from a strategic perspective. What we would end up with then is a tree like this, where the operational scenarios are linked to strategic nodes, long-term nodes, and you get the end of horizons in these different places in the tree. And of course you can do a lot of fancy stuff with end of horizon descriptions in such a setting, but this is the trick, and it means that you have some discoupling between the curves of dimensionality in the short run and in the long run. You could of course add multi-state trees also in each of the long-term nodes in this case. And if you only use short-term uncertainty then, so the long-term uncertainty is gone, this is a sequence of decisions in a strategic deterministic strategic perspective. You make a sequence of decisions for your long-term level, and you link the short-term scenarios below that to calculate the consequences in the short run of your long-term strategic deterministic plan, as opposed to the situation where you also add long-term uncertainty. So in this first case study, it's only short-term uncertainty, and that's in principle a two-stage stochastic program that I'm showing you for the next few slides. And what we do then, of course, filling this with data is critical. So we want to capture correlations. I think you would like to capture some of the moments like expectation and variation, maybe even more. But it's critical to capture correlations. And you have the time correlation, so we sample a point in time. So this would be, for example, Germany, the load, and we then use a scenario which consists of 168 or more sequential hours. And we sample another point in time, and we include that into the scenario trees. But we used exactly the same time periods for the wind profile, for the solar profile, and we used exactly the same time slices for other geographical locations. In that respect, we capture time correlations, we capture correlations between different variables, and we capture geographical correlations. Then we use a moment matching type of algorithm to pick scenario trees that have similar properties to the original data sets without destroying those properties. So that's the background, if you look at another type of background, which data do we put in? So in this particular study, we put in a moderate increase in electricity demand in Europe based on EU reference scenarios, and we put in moderate development in fuel prices into the model. You can always argue about those things, but more important, in the same time period, this is the emission reductions that we put in as a cap in the model. So that's a cap that is gradually increasing in respect that emissions go to zero. Even more controversial, battery investment costs. So this is the curve we're using at the moment, and solar PV investment costs. So no matter what you use, people seem to protest on these kind of curves, but and it's highly influencing the results, of course. I don't think these are too bad in the respect that at one point they need to be more flat than today, unless some really new technology comes up, and that would add, of course, technology uncertainty in the long run, which could be a nice feature. So this is the type of results that we get. So this is in a baseline scenario with 90% emission reductions. Carbon capture and storage is a feasible technology in the power sector, and that's arguable. But in that case, the solar would have 46% of the capacity and 26% of the generation. And this kind of numbers comes out because we model the market clearing hour by hour in this case. The wind would be 24 and 27, and natural gas with CCS 10 and 26, and there you get the picture about how important this controllability and the ability to schedule the generation will be. I just want for reference to show the situation without carbon capture and storage, and we see a new life for nuclear power coming in this kind of situation. So in the case of carbon capture and storage, nuclear will be replaced, at least with the cost levels we see today, with these other technologies. Without carbon capture and storage, the amount of natural gas used by the model is reduced by 50%, and nuclear reappears. So where does it happen? Yeah, so this is pictures that we would get out of the model. So this is the baseline again. Very funny result. You look at solar in the UK, and you look at some other countries like Norway, where you have hydropower and wind. So all in all, you can always argue this is just one possible story about the future. This is not the future. I mean, this is based on some input we give to the model, and it's one possible future. I'll come back to that solar in the UK, and it has a reasonable explanation. This would be the situation without carbon capture and storage. I like very much the nuclear reappearing in France. We banned it in Germany in the model, and it's built in France instead, which is, of course, reasonable. Then the explanation about the solar in the UK. So look at this one. So this would be the link between Ireland and the UK in 2050. So basically what the model does, it says it blows more in Ireland, the sun isn't shining in any of those two countries, but it's nice to have solar PV anyway. So let's build the wind in Ireland and build the solar in the UK, and then we build a lot of transmission between those friendly countries because they're probably going to agree. So this model doesn't consider Brexit or any other political issues, but that's the type of results you get. The model isn't that intelligent that it can realize that this is not very practical. In my opinion, this points more at a challenge than a solution. If you look at the numbers, it suggests investing in import-export capacities between European countries, which is 600% more than today and 800% more than today, with and without carbon capture and storage. It's very hard to believe. But this model includes batteries, it includes demand response, and it still says you should build transmission. And that just points at one major dilemma for the European Commission. If you want to have renewables with that higher volume, you need to do something. And the solution that is not included in the models, let's hope that will be a good one, is system integration, sector coupling, where you would start looking at the links between the heat system and the power system and the natural gas system. So that's not included in the model, and let's hope that that could be a good solution, because personally I think it will be tough to build that much transmission. But remember, the reason the model does it is because of the correlations, and it recognizes that demand response, well, you could ask the active consumer to turn down consumption for a day, for 2 weeks, when the wind stops blowing, probably not. So I'll jump then to, well, this is the Norwegian situation, so we don't have problems with too little flexibility, but we have this problem. It's the electric vehicles that comes in, and you see a demand peak going like that at 5 o'clock in the afternoon. So that's what demand response could do something about. The wind stops blowing, that's not a solution. So I have a few slides on demand response as well, since that's of very high interest, and many people would say that transmission is not the solution, demand response is the solution. This is not what our analysis shows, but we added, in this case, 7 flexible load types and 3 economic sectors into the model that uses demand response, and the 2 types of demand response we add is shiftable volume loads, so you could take a load and shift it out over some hours, and you could curtail some load, both at a cost. And it's heating and some industrial processes, air condition, cooling water, washing equipment, and some heat storages, and yeah, shedding load in process industry. So there are these types, and of course they come with an investment cost, they come with an operation and maintenance cost, and they come with some efficiencies in doing this. And in fact, we also model the fact that the efficiency of some processes go down when you shift load in time. And you get pictures like this. So of course this will very much depend also on the cost levels, but you see that investments in demand response comes in countries like France, like UK, like Germany, and Spain, and to lesser degrees also in some other countries. So how does it work? So this would be the wind production and the solar production, and the grey one is the original residual load after those two, and the yellow one would be the new residual load. So you see it's shaving those peaks as you would expect, and it's filling out the valleys like you would expect. So that's what the model does. But of course this cannot handle the situation when the wind doesn't blow, and that's the reason why we don't get a full effect of the demand response. What demand response does, it would substitute out some technologies, like natural gas with CCS would get less popular when you have demand response. For coal, it doesn't affect it, at least in our model. For renewables, it seems to go well with solar, so solar investments would increase, while some of the wind investments would first decrease and then go up again later. So that's the kind of effects that we could study in a model like that, and of course it all depends very much on the data we provide to the model and the correlations that we put into the model. And this would be the pump hydro storage not affected, and the battery storage. So a very clear example is that this demand response is an alternative to battery storage in that respect. So that's the short run, and let's move over to the long-term uncertainty. So I hope that gives a clear picture of what the model does when you include short-term uncertainty into it. And we did include long-term uncertainty on some of these learning curves and fuel costs. And of course it affects the expected cost of building the European power system zero emission. But we found out it doesn't affect that much the technology mix. I think this is something we need to revisit because it has also something to do with the timing and the lag between the point in time when a decision is made and when the investment comes into active generation and is available, and that could be a time lag. What we found with policy uncertainty was that exactly how we model this time lag is critical. And if you recapture then the type of trees that they're using long-term scenarios and short-term scenarios. Short-term scenarios represented by a number of operational hours. And the long-term tree in this case we model in a quite undiplomatic way. We say that the policy uncertainty is regarding the ambitions of the European Commission in terms of meeting the climate obligations. So at each point in time we model a small probability that the European Commission will deviate from the zero emission target for the power system. So that would mean that at this point in time there is a likelihood that you would slightly reduce the ambition, and you could next point in time continue to reduce that ambition and maybe. While the majority of the uncertainty weight is put on the situation where you would actually go towards zero emissions, in this case 34% will be put on that scenario, and then with very small probabilities for each of the scenarios indicating the probability that the Commission would deviate from the long-term target. So that's what is included in the long-term tree, and the short-term trees are exactly like I showed you before. So you get a number of test instances then. So of course there's a limit to what you can do computationally in a single computer. So basically we implemented this in a progressive hedging type of algorithm and used distributed processing, and typically one processor per long-term scenario. So the test instances, in this case it's 72 operational hours. So one scenario going over 5 years has 72 operational hours. It's two short-term scenarios, so each branching point has two branches. It's 4 long-term scenarios, that means it branches in 2 stages, and we have a branching factor of 2 again. So that's the smallest instances, and I have 5 million rows and 4 million variables in this case. So the largest ones would be more in this scale, where we have 720 operational hours per scenario on 3 scenarios, and 81 long-term scenarios. So we have 81 of those individual scenarios in the long run, and that means we are branching on stages 3, 5, 7, 8, and that's 5 years between each of them, and a branching factor of 3. So that would be 760 million, so 1.6 billion rows, and 1.2 billion variables. So this just points at some of the computational challenges you're facing when you want to combine, of course, long-term uncertainty and short-term uncertainty into those kind of models. With direct solving, sort of the place, I will not say this, it's not possible to solve larger instances than this, but at least with these 720 operational hours, we could solve for this instance with 3 and 4, so that would be this one with 3 short-term scenarios and 4 long-term scenarios, and a branching factor of 2. So the larger ones is only solved using the progressive hedging algorithm, and it's typically solved using 73 hours and using 81 processors in doing so. So 81 processors for 70 hours is basically what you need to solve something like this, and an implementation of some decomposition algorithm, for example progressive hedging. And I think it's a fair question at this stage to ask, so what do you get from spending so much computational power on modeling the long-term uncertainty? And we did look at the value of the stochastic solution. I think it would not be fair to compare the value of the stochastic solution in the traditional way, where we take the deterministic solution and we plug it into the stochastic scenario tree. So what we did was a rolling horizon deterministic model, where we gradually updated the information in the long-term part. So the deterministic model, I have to say, it also included short-term uncertainties. It was only deterministic in the long-run uncertainty. So we basically did a rolling horizon in the long-run uncertainty, and we get effects ranging from 0 in the smallest instances up to some close to 10% in the largest instances. What would that mean? It means that if you believe that the long-term scenario 3 is correct, that this political uncertainty is existing, and you would not actually take that into consideration when you're investing, you would not be well off compared to the stochastic programmer that makes the investment decision. It's an alternative question that could be asked, that we didn't ask, but we need to ask that before we write the paper, is what is the cost of policy uncertainty? So if you could reduce that policy uncertainty, how much would that benefit society? And that is not answered by this analysis, but it's fairly easy to answer that question as well. And I think that's a clear indication that we would benefit from considering this. We did not answer the question, how much do you lose by having this policy uncertainty included, but my guess is substantial. And then a good question would be, so what is the qualitative differences between this rolling horizon deterministic approach and the stochastic programming approach? And this would be investment costs, the blue one, and operational costs in the rolling horizon and stochastic programming respectively. And these two are sort of fixed investments, so the model starts investing heavily in 2020 and onward, and you see also then we have allowed the model to invest, so we have let it invest in 10-year intervals in this case to save also computational burdens. So what you see is it doesn't look that different, but you see that the stochastic model in many cases invests slightly more, and in many cases have fairly similar operational costs, except in this time stage, 2045. What happens there is you get an enormous cost in the rolling horizon model, and the explanation is quite interesting. It's basically at that time you get an enormous curtailment of load. So basically with the emission cap that you put in and the investments that you did earlier in the process, you are not able to meet demand. You have to make the choice, do I want to meet demand or do I want to meet the emission cap? So we don't give that choice to the model, we say you have to meet emission cap, and that means you have to curtail demand. And what happens is, if we remove this time lag between the point in time when we make the decision and the time when capacity is available, basically the two models behave fairly equal. In that case, the rolling horizon model is able to readjust as it's learning what is happening. In the cases where we introduce a time lag of 5 years from the time when you make an investment decision in a flexible technology like natural gas with CCS until it is available, you get this kind of situation. In that case, the rolling horizon model thinks everything is good. It comes to 2045 and it figures out, well, this was really a dry year. There is not so much hydropower in Norway. The wind is not blowing that much either. And I can use natural gas with carbon capture and storage, but I didn't invest in that. And at that point, you get the curtailments. And that's the kind of risk that we would be facing in such a situation, and the main benefits, as we have observed so far, from using a long-term stochastic model. My guess is what would happen in reality is, of course, you would not do the curtailment, you would just don't care about the emission cap. And that would be the solution. Fundamental differences is, you see the stochastic model, so this would be the positive part of this would be increased investments in the stochastic model, so it invests more in storage peak capacity and storage energy capacity, and it invests less in high CO2 intensive technologies, and invests slightly more in low CO2 intensive technologies. And in particular, you see that in 2040 the stochastic model invests much more in storage, and that's maybe the explanation why you get the curtailments in the rolling horizon model, that the stochastic model realized that something is going on. And is it 2045 a magical year? No. 2045 is the year when the sampling routines that we used made a sequence of dry years with little wind. And that could have happened much before, or it could happen much later. In a stochastic model like this, it will happen. And this is exactly what you would get. If we would include a much higher number of scenarios, it would probably happen very often. But in this kind of model, it happens at this stage. So I see it's time to do the summary, and I think new technologies increase the need for flexibility. That's one of the major observations when we had short-term uncertainty and emission cap. New technologies increase the potential for providing flexibility from the demand side, but it doesn't solve the problem by far. And the model would suggest investing in a lot of transmission. Still, demand response would put pressure on some technologies like batteries. And both long-term and short-term uncertainty seems to matter. I think the way you structure a long-term uncertainty, for example, if you make every investment available immediately, long-term uncertainty plays a lesser role in the analysis. But if you think there is a time lag, you need models that are good at looking ahead in time and considering the uncertainty you are facing. So in the long term, policy uncertainty affects the investments, and I think more work is needed to look at how could effects of policy uncertainty be reduced, and also maybe more work to understand the effects of policy uncertainty. So far, we didn't find many. I don't think we found any publications at all that combines long-term and short-term uncertainty into this type of analysis, unless, in fact, we wrote a book chapter 10 years ago ourselves, but I cannot remember if we actually wrote that book chapter, but have to find out that. But if you would have any suggestions for other type of references that do this kind of combinations, I will be very happy to see them. Yes, thank you.
Thank you, Asgeir, for an interesting talk, and from the chair's perspective, another very well-timed talk. People from speaking Thursday and Friday know the latter part of that. And I'm very pleased to hand over to Andy to act as nemesis.
I don't know how I get to be a nemesis twice, but maybe that's my scheduling. But very
it was either you producing the spreadsheet or me making a typo in invitation.
So a very interesting talk, Asgeir, and I've seen your work on this, of course, in previous talks, and I think it's great what you're doing in terms of the degree of detail and comprehensive modelling you put into it. It's really impressive. So I guess one of the questions I have is about Europe. It's we're doing similar work in New Zealand, I should say. We are an island, two islands. Well, Europe is an island, as you say, but an island made of different countries. And each country will actually probably want its own policy or policies which may serve its own interests.
Yep.
So is there a way of kind of reconciling those individual interests somehow? You know, the social planning model here may be good for one country and not so good for another. So how do you kind of trade those things off?
I think these are the central questions in terms of how do you do the kind of profit sharing that you would benefit. For example, we have this discussion in Norway building cables to Germany or the UK, and in some cases it's clear that if this is beneficial for society, it will be a question about how do you share the cake in that respect. But this is one of the uses in this kind of research for us, bringing that into the policymakers, saying that in the long run, if you look at the cooperative Europe, it's clear that there will be need for some joint efforts. For example, if you look at the North Sea region, where a lot of this offshore wind could be built in the interface between UK and Germany, Netherlands, Belgium, Norway. It's clear that in Norway we don't need that energy, but we may benefit if our neighbors would want to use that energy. And I don't think that's likely to happen unless you actually start making long-term policy that say we would jointly develop this kind of region, and we would have agreements on how to share the benefits on that. And that brings us into game theory and market design and regulation. And it's highly interesting to do work on
I guess my question: who's using? Is anyone using this model that you developed? Or is it
we are mostly using it, but we have used it to provide advice into the European Parliament for the carbon capture and storage strategies. I'm not sure if anyone would like to take the honor of that, in fact, but at least it's been used by the Zero Emission Platform, which is one of these technology and innovation platforms, to do all the analysis, suggesting how an incentive scheme for carbon capture and storage for industry and power could be taken into use. So that's a very nice application of stochastic optimization, I have to say, when you can give advice to European Parliament. If they listen, that's a very different story. And the same with Norwegian policymakers. When we give advice on how to approach the North Sea area, currently there is no long-term policy for the North Sea area, but our hope is, and we'll present that to the Norwegian Ministry next week in a conference in Trondheim, that at one point I would start making a long-term strategy with neighboring countries for how to actually approach that. And then at least we have this kind of, let's call it fact-based approach, where at least if you believe in the input data, there are some consistent stories to be told about long-term. But I think it's a fair question. How are these kind of massive computational requirements that is needed? How can these more easily be taken into use? And I think from our perspective it's to provide policy papers, position papers, where we don't take a political position, but we give some facts about input and the possible consequences.
Okay, any questions from the room? Lots of questions from the floor.
So I had kind of a similar question, but it's kind of more narrowed down, specifically in terms of transmission. So clearly right now these interconnectors do exist. So can you enlighten us on who has funded them and how does the pricing methodology on these transmission cables work?
Yeah, so a typical example would be if you build a cable between Norway and Germany today, it would typically be a joint venture where the profits of that cable would be shared. It's supposed to be funded by the congestion rent of that cable because of the implicit auctions that are made in the market. So for the Norwegian players, this would mean that the market gets larger and the price will go up slightly, and opposite on the German side you would get more supply in, and the congestion rent would ideally pay the cable, and you would say that if there is a profit it would be shared between the two countries. But of course this is a highly interesting question, even when you assume that there is perfect competition in both countries. It's not necessarily so that even if the producers and the consumers in Norway in total gets a better situation, it's for sure such that in many cases the consumer would get worse off and the producers would get better off, and this is exactly what we're looking into at the moment, how to put up sharing mechanisms that would make all parties happy. So I mean, part of this is welfare transfer, and you would like to have welfare transfer that is not distorting the optimal market allocation. But and of course this model doesn't answer how to do that, but it gives some indications on where you would like to move.
Yeah.
Thanks, Asgeir. So it was nice your slide in the middle with these huge numbers in terms of transmission expansion. After you played putting a cap on emissions, why didn't you also try to play this game of putting some cap on the transmission expansion?
We did that in fact, but I didn't have time to present that. And what you see if you put a cap on transmission, and it's very interesting, the need for renewables go down, and the need for batteries go down, and the need for centralized solutions go up. And that's a quite interesting observation as well, that renewables and transmission in this kind of models go hand in hand.
Yeah, because I think it's nice for policymakers that they see what would be the consequence if they cannot do this kind of transmission expansion, right?
That's a good observation.
So we had a question before about, I don't know, the validity, if you like, of the competition model in Europe, which is effectively decentralized but somehow coordinated badly. So against that background and thinking about what policymakers are able to do, particularly when they're semi-coordinated, how reasonable is a model that looks at averages, a risk-neutral model? Because he's playing averages over 50 years.
Yeah, so that's a very interesting topic as well, in my opinion, to look at how risk aversions among parts of these players would affect the solution. You could say that there's no reason to be risk averse. We would like to have a zero emission power system. Let's just do it, and we are risk neutral in that respect. The main risk is in the climate. But if you look at
it's like all the stochastic programming. You're going to end up on a particular realization.
Exactly. But I think it's one thing we have been discussing as well, introducing ambiguity on for example, the long-term uncertainty, and do more risk-averse approach on that, and assuming risk neutrality in the short run, for example, is very nice.
Very nice. Thank you so much.
Well, I have a policy question. Because, well, you assumed that the emissions should go to zero, but your model gives the cost. And there's obviously law of diminishing returns, so it costs more and more to reduce emissions. So would your model could possibly be used to get a break-even point when comparing the cost of a marginal reduction in emissions compared to other sectors which would do exactly the same thing? Because maybe it does not make sense to go to zero because it's far too expensive. Maybe it makes sense to do something else regarding transport, heating, whatever.
Yeah.
So have you tried to do something like that?
What we can get out of the model is the shadow prices on this constraint with the caps, and we can get a curve for the CO2 price. And the reason I don't show it, I think these are highly controversial, of course, these prices that you get out of these models. I mean, then you boil all the uncertainty in the short run and long run into a power price or a CO2 price. It's possible to do, but that would possibly be the two most uncertain numbers that come out of a model like this.
There will be some numbers.
There will be some numbers indeed.
At the moment, there are no numbers.
Yeah. So, yeah.
Yeah, so it was very interesting that such a study, like other studies based on scenario 3s, essentially are based on some particular discretization of the uncertainty space.
Exactly.
And you could argue that many other different discretizations would be as valuable. So my question is, have you any means to estimate error bars?
Yeah, so what we're doing at the moment we have been doing this previously in other types of stochastic energy system models like the TIMES model, doing stability analysis, but we're currently working on a paper also for this model where we're doing stability analysis on the number of scenarios you need to capture the uncertainty. So basically what we do at this point is, instead of generating one scenario tree, we generate 100 scenario trees, and then we pick the one with statistical properties that match the most the original historical data. But we would like, of course, to learn more about how stable are all those models. If we generated a new scenario tree with exactly the same kind of structure, would we get a completely different solution? And in many cases, I would guess that the answer would be yes. You would need to do stability tests to make sure that this is not depending on the tree and structure you choose, but on the real underlying data.
Right, I think we've got. Should we collect? I think Stan, Ben, and sorry, I wasn't sure whether you were just waving a hand around. Should we just not got too much longer? And this isn't just lunch; it's the free afternoon that people are being kept back from. But should we just collect Stan and Ben's questions? There's two, and then
very quickly, your rolling horizon bridge, is that based on taking expectations?
Yeah. So then we let's roll through the long-term tree, and at each point in the long-term tree we do an expectation of long-term uncertainty, but keep the short-term uncertainty, and then we resolve the model for the remaining horizon.
Suboptimality there might result from asymmetry of the risks involved.
Yeah. So since you're being risk neutral in this case, of course, it's then adapting to the short-term uncertainty that you're facing, and definitely you could have some asymmetries because, I mean, the trees are sampled, so you don't know exactly how they would look. Yeah.
I think this is short too. So in the VSS calculation, you assume that the stochastic tree is a true tree. So you could do a rolling stochastic also, where you're doing out of sample scenarios.
Indeed.
So testing. So you make your initial decisions based on either the rolling one, the rolling deterministic one, or the rolling stochastic one. Roll forward, generate a new tree, and so forth. I'm wondering whether the VSS would persist in that case, you think?
So if you would have a scenario tree that is large enough to provide stability, and let's hope we have that, then I don't think it would change if you do a rolling horizon stochastic or not. Ideally, it shouldn't change in that case. But I think it's a fair question, the first one here, that the deterministic model is probably much more prone to do mistakes in a rolling horizon where you have sampled a tree like this, and would need if you would have a larger tree, I think we are doing the deterministic model a disfavor by having a small tree in.
Yeah, we found that for the Western North America, 3 to 5 appropriately chosen scenarios on this rolling forward type of out of sample analysis does much better than the rolling horizon deterministic. That there's something about the solution, so you get that they do well, even if the soccer ball doesn't come exactly where you think it might come in your 3 scenarios. So.
Yeah, so I think this is much to do with the inherent flexibility that are in some systems. So if you have a lot of flexibility from the strategic side, the rolling horizon deterministic could do really well. But if you have the time lags like the ones we introduced here, which I think are realistic, that when you make a decision it takes you some years before the capacity is available, the deterministic models start losing.
Anyway, before we thank Asgeir again, are there any notices about tonight?
The dinner is at Westminster College at 7:30. There is a map online. We should get there about 7:20. And dress is semi-formal. How we dressed at the moment. Yeah. Apart from that, that's it. Yeah. Well, it's about 5 minutes walk from here. I'll be leaving here if you want to come with me at about 4:15.
Okay, so we should thank Asgeir again and enjoy the free afternoon.